Good afternoon. Welcome to lecture 79 and 80 on the course Thermodynamics of Materials. We will first complete the last problem of the third class test, namely problem 4 concluding part. So first we complete problem 4 class test. Problem last class. Okay. Problem 4 concluding part. We obtain this. Actually, the equilibrium constant is pH2. We obtained this. Okay, we obtained K500. K500 is nothing but 0 point is actually pH2 by pH2 equilibrium. Equilibrium is 0.011. We reached up to this point in the last class. Last class actually on February. That is 3-4 days ago, February. That was a Friday. That was Friday, 14th, February 14th. On February 14th, we actually achieved this in the lecture 77 and 78. This was the last line that we arrived at. But today I just want to complete. What is the percentage? We are required to give the percentage. What is the percentage? H2O, very easy. Is this 0.011 divided by 1.011 times 100. It is actually giving you 1.09%. Similarly, percentage hydrogen is 1 by 1.011 times 100. It is actually gives you 98.91%. So we can write up. Hence, this is the required composition of H2 gaseous mixture of H2 gaseous mixture in equilibrium with SN, tin and tin dioxide, SnO2 at 500 Kelvin. Answer. So with this we have completed third class test. Okay, third class test solution. Now another point, actually, before I take up today, actually we have scheduled to take up the thermodynamics of solution. So for this, okay, before this, I want to cover one point or clarify one confusing point. So this is okay. This is over. Right here, third class test solution over. Third class test solution over. Next, actually, now we actually take up another one. Another discussion on phase equilibrium. Phase equilibrium. This the impact of the presence of an inert gas on the phase equilibrium phase equilibria of a single component system. On the phase equilibria, I will mention this. Well, phase equilibria and its consistency and its consistency with the Gibbs phase rule. This is actually this will be demonstrated now. The importance or influence or impact of the presence of an inert gas. So, start. Consider the following phase diagram of a single component system. A single component system zinc से so this is the given saturated vapor pressure. The saturated vapor pressure liquid zinc at 700 Kelvin is 2.6 times 10 to the minus 4. 2.6 times 10 power minus 4 atmosphere. So I am sketching the diagram now. As you know, single component easy. This is P axis in atmosphere. The temperature axis, Kelvin. And if you draw this diagram, this is zinc solid. This is zinc liquid, zinc vapor, as we know. So now you consider this temperature of this is the temperature of say 700 Kelvin. 700. And what is the corresponding vapor pressure? All for zinc liquid, zinc vapor, this vapor pressure is 2.6 times 10 to the power minus 4. Very small vapor pressure. So if we take up the so here we can actually consider this. Let us sketch this. So suppose this point is, this state is x. Give it sketch. What is the sketch here? This is, suppose this is your, you have zinc liquid and zinc vapor. What is the total pressure? P right here is the total pressure. Total pressure. Total pressure. It can be capital, okay, uppercase P also. And zinc vapor, what is the pressure? P Zn is, as we know, 2.6 times 10 to the power minus 4 atmosphere. What is the total pressure? That is also same, because only one gas species, 2.6 times 10 to the power minus 4. And what is the temperature? This is arbitrarily chosen. Temperature is 700 Kelvin with the thermostat arrangement. So this temperature is arbitrarily chosen. Or arbitrarily or independently, arbitrarily, that is independently chosen. Independently chosen. So if we apply the phase rule, Gibbs phase rule, let's see, write this, the Gibbs phase rule. Achha, note one thing, here, achha, I'm writing here, note, Gibbs phase rule, the Gibbs phase rule will be discussed in details later on, after we have completed solution thermodynamics. Anyway, so this, note this point. So I'm writing again, F is C minus P plus 2, the Gibbs phase rule. Here we use this rule, okay. And now what is the, how many degrees of freedom we have applied? We have applied arbitrarily, independently. Freedom means independently. 1. What is that? Temperature. 1. And pressure we have not fixed. Pressure is, note, P is automatically fixed. So no freedom. This is no freedom. So one freedom applied, because this is the equilibrium vapor pressure, it cannot be otherwise. So we have to maintain this total pressure. So let us see, degree of freedom is 1, we have applied in the form of temperature. This I am writing, this is the temperature. Component is what? It is 1 component, zinc is 1. How many phases? Suppose we want to check Right here, C is 1. Who is that? Zinc. What is the value of P? P is 2. Two phases present, and we see here two phases present. So P is 2. So two phases present at equilibrium. Namely, who are these? Namely, zinc liquid and zinc vapor. Two phases present. So consistent with the phase rule. So what we observe here is consistent with the phase rule. This is actually say figure 1. If I may write it, figure 1. Figure 1 depicting state X. State X. State X. This state. This is shown by this liquid vapor coexisting. Next is now the complication starts. Now, if we next, okay, now if we raise the external pressure, which I say P, raise means change. When I change means this is independently. Change external pressure to a higher value of 0.5 atmosphere say independently write this, consider this independently change means any value we choose. So what value I have chosen? 0.5. So it is another freedom. So in that case, what is the diagram like? I would say I'll give you this. In that case, 2 degrees of freedom are applied. 2 degrees, who are they? Temperature as before already, now pressure, total pressure. Total, change the external pressure or total pressure, okay? Tp, in that case, 2 degrees of freedom are applied, resulting in the elimination of a phase. Which is zinc vapor. Zinc vapor will be eliminated. What is the figure? Let me draw the figure that will be best. Let me draw the figure. Zinc liquid alone present now. What is the pressure? P is 0.5 atmosphere. Temperature as before 700 Kelvin. So you see freedom 1, freedom 2, only one phase elimination. This is consistent with the phase rule. This is consistent with the phase rule. How? Again try. Let us see. F is, it is constant. How? F is C minus P plus 2. F, how many? F this time, previously it was 1 temperature alone, but this time it is 2. What are the temperature, pressure? Is C again still zinc components, single component system 1 minus P plus 2. This leads to what? P is 1, and we see that zinc liquid alone is present. Zinc liquid, no vapor. This is also observed from the figure also, phase diagram. How? Say this is the point where zinc liquid, zinc vapor coexist, X. So let us write, this is figure 2. I am writing right hand side. Figure 2, state Y. I am showing you state Y. How? Just increase this, increase this, increase this to say, supposing this is the not to scale low, this is the value of 0.5 atmosphere. The moment it is raised to this value, I can give an arrow maybe, raised to this value, this is a state Y. System lands onto point Y or state Y. Which phase is present? Zinc liquid. So zinc liquid is shown and it is consistent. So so these two cases I have shown. More important and intriguing is the presence of an inert gas. This I will take up as the last case, last part of the discussion. So can I remove this? Okay. So now, so I have to remove a part. I have to remove a part. Okay. Which part I will remove? Actually, I am removing the top. This top actually no more required. It is already over. This is question. Next case is a question. So we see when degrees of freedom are increased, number of phases are less, fewer. So 1 fewer at equilibrium, 2 to 1. So next case, obviously, it actually comes to our mind that is it anyhow possible? Is it anyhow possible? Is it anyhow possible to have both zinc liquid and zinc vapor coexisting? Zinc liquid and zinc vapor coexisting with the application of 2 degrees of freedom, 2 degrees of freedom. This is the last case. Answer is yes, it is possible. Answer, yes, it is possible. It is possible with the introduction of an inert gas, of an inert gas, say argon. This is okay. Let us see how I am sketching this. Then you have this is figure 2. This is a figure 3 coming. You have zinc liquid, argon, gas, zinc vapor. All zinc liquid, zinc vapor coexist. How? With the same 2 degrees of freedom, means without changing anything from figure 2. Same. Only means total pressure is same. So P is still what? 0.5 atmosphere. Same as here. And temperature same. Temperature same. What temperature? 700 Kelvin. So here what is the zinc vapor pressure? PZN. Actually, I may write somewhere PZN I have written. This PZN is also note here. PZN is PZN 0 also. Okay. This is saturated vapor pressure of pure liquid zinc, PZN 0 also. So sometimes we write PZN only, but it is PZN is how much? Again, it cannot be changed for this temperature, which is 2.6 times 10 to the minus 4, 10 power minus 4 atmosphere. So what is the pressure of argon? Obviously, the balance 0.5 minus 2.6 times 10 to the power minus 4 is essentially 0.5, but this is the distribution. So this is actually, so we see our problem is solved. Zinc liquid and zinc vapor coexist with how many freedom? Freedom 1, freedom 2, 2 degrees of freedom. So I write here, this is 2 degrees of 2 degrees of freedom applied, 2d of applied figure 3, 2 degree of freedom applied here, applied here. Then who is this? Temperature and pressure. Again applied here, again temperature, pressure, again. But we have zinc liquid. Okay. Now what is the phase rule explanation? Phase rule. How will you understand this? Should be supported by the Gibbs phase rule. Phase rule application. Let us do this. F is C minus P plus 2. As you know, F is 2 already. Again, shall I write? Again, I have already written 2, temperature, pressure. Component, I'm just writing, component is okay. What is the component here? That is important change. Most important change. That's why this case is interesting. And okay, we should learn this. C is no more. C is 1 here. C is 1 there. C is where? 1. But this time it is not 1. This is, and that makes the difference. Who are there? Tell me. Zinc, of course, and zinc and argon. So substitute P, how many? We want to know. This leads to P is how many? 2. Who are there? Zinc liquid, the liquid phase, and gas phase. You don't need this anymore. And gas phase containing zinc vapor. This is all about what I wanted to cover about the phase equilibrium and the effect of inert gas on this phase equilibrium. Okay, and number of phases that are present, how that will be, how this number will be governed by this, introduction of inert gas. This was discussed. So this is over. Anything else? I don't think. if you have any questions, you can ask me. Okay, this is the thing that I wanted to tell you. Okay. Okay, this part is over. This part is over. So now we have actually covered phase equilibrium as well as the third class test question paper. So we will actually move to the next big topic, which is solution thermodynamics. So next is, let us start from this place. So next chapter is solution thermodynamics. So it will require number of classes. Okay, 4, 5. Let us see how many it is required, and we will keep on the complicated part of solution thermodynamics. First of all, as introduction today, introduction. In the introduction, I would say, why is solution thermodynamics important? Question is, why is solution thermodynamics important? Two way. First, I say chemical metallurgy domain. In chemical metallurgy field, you follow this. How this solution thermodynamics will be important and will modify the result. Consider this reaction. Consider the reaction. Then I will consider physical metallurgy next. Consider the reaction or you can consider equilibrium. Metal plus O2 goes to MO2. What I should write here? M pure to O2 gas, as you know, MO2 pure. They can be solids or liquids. We don't bother ourselves with this, whether it is solid or liquid. Okay, it's pure. That is important. Now, what is the equilibrium constant? Is delta G02, you recall? That is equilibrium constant. What is this? AMO2, AO2 means PO2, you know, activity of gas. So this is being pure 1. So what is 1 by PO2? So after putting the value of delta G0 and K, suppose PO2 equilibrium at the temperature T turns out to be 10 to the power minus 5 atmosphere, say. Next question is, these are all pure condensed phase. Note pure condensed phase. Note here, pure condensed phases are involved. Pure condensed phases are involved. Involved. Are involved. Up to assignment number 7, up to this point, we have considered only pure condensed phase. Now we'll consider the components are impure. Solution. Impure in mixture, either impure or mixture. So many ways we say solution, mixture, or say alloy. So what will happen when the metal or metal oxide are in solution state, impure state. So this will take up. So when this pure, so you write here purity equilibrium. You can write also MO2, both pure. Next, consider M impure. M impure. Plus O2 gas, O2 pure. We don't complicate this part. M impure how? Like Mn alloy. So Mn alloy. Okay, e.g. for example, silicon and silicon iron alloy. M is silicon, N is iron cell. So what will happen to this now? Again you start delta G0 KT. Even temperature, assign the temperature 800, 900. Delta G0 gives you again K. Same delta G0 because it refers to standard state. Standard state, although this is impure, but when we consider delta G0, we have to consider standard means pure state. So remain same. Delta G0 cannot be changed. Okay. The reaction may be impure, that I will use. That we will use when it is the impurity, how it will be considered in the equilibrium expression. Follow this. Delta G0 is KT is what? Activity of MO2. Am I right? Activity of M PO2. Acha. I write here before it is late. We interchangeably use solution, mixture, or alloy. Just note this, okay? So impure, these are all impure. So you use, okay, this okay, or impure or solution, mixture, or alloy for impure state, for an impure state. So now again MO2 is, supposing that MO2 is producing pure, may not, but we simplify here. Suppose it is pure, still we want to see what is the effect of metal being impure. So what shall I write here? What is activity? It is impure. For pure substance, activity is 1. This is now because impure, less than 1. It is impure, less than 1. So what is the result? This is unchanged. Remember, this unchanged. Remember, standard state is standard state. Standard state is the free energy of this state standard, this state standard, this state standard. So that value unchanged is minus R3 ln K, gives you K, which is unchanged as long as temperature is fixed. That we consider, of course. So what will happen here? This is, if this is less than 1, so if you follow this, what is the consequence? If this decreases, this PO2 will increase. So PO2 equilibrium under which condition? MO2 again, but only thing M is impure state. Is what? Since this decreases, left hand side constant, denominator decreases, one term decreases, the other term increases. So PO2 will be greater than this. Atmosphere, say 10 to the minus 4 atmosphere. This is the consequence. This is the chemical aspect of solution study. When it is in solution equilibrium value, what does it mean? See, clearly you see, it requires both pure, it requires a oxygen just greater than 10 to the power minus 5. Its critical value is 10 to the minus 5. Greater than this, metal will be oxidized. But in this case, just greater than 10 to the power minus 5 may not be enough. Suppose it is 10 point minus 4.5, greater than, but has not exceeded 10 to the minus 4. So there is no oxidation. So it is more protected. Metal, when metal is impure state or alloy state, solution state, it is more protected from oxidation. So that's why we actually often oxidation or corrosion. So we prefer alloys, alloyed metal rather than pure metal. So that's why we study metallurgy alloys. Metals alloys. Alloys. So this is chemically relatively more stable. But it will be oxidized also if it is exceeded 10 to the minus 4. But this is more difficult than this. Now next case is still next. Obviously guess what I should say. Consider still next consider M pure. I don't change this. Pure plus oxygen gas. Consider the reaction. Consider equilibrium rather. Equilibrium is MO2 impure. This time MO2 is impure. Example is so Eg MO2 is impure. How? MO2 NO2 or say MO2 impure. Okay, MO2 and another things. Okay, example I am giving you: silica calcium oxide. The base silica, okay, is taken up in the by this calcium oxide forming a slag. Okay, so this is basic character, this is acid. So anyway, so if we consider this, what will happen? Silica calcium oxide, so MO2, okay, right, MO2 X. So MO2 is silica, X is calcium oxide. Then what will happen? Again start, delta G0 is Kt from minus RTL and K. Delta leads to Kt is activity of MO2 activity of M PO2. What is this value? This time this is pure. See, this is pure. So what is this? Since impure means less than 1. Pure has the maximum activity. This is because of vapor pressure relationship. So fugacity. So it is less than, this we will discuss today. Discuss activity of today or tomorrow. It is less than 1. So what is the consequence? Tell me. Again you see, refer to this line. So if these are all 1, PO2 was this value, but this time this has been decreased. This is decreased. So as a result, PO2 will decrease. So this leads to PO2 equilibrium, which temperature T, temperature must be given for equilibrium, metal oxide, and underscore means it is impure. Here M is impure, here both pure. So what is this value? You can guess. Since it is less than 1, this is unchanged as before. Standard state cannot be changed unless we use alternative standard state. So we are not considering this. So unchanged PO2 will be, what is the PO2 will be? You have to comment this. This decreases means PO2 will decrease from 10 to the minus 5 atmosphere. E.g. say 10 to the minus 6 atmosphere. So what will happen? Now if you compare this, so now suppose comparing with the pure condensed space situation, if the product produced at a lower activity, means impure state, so like M is silicon, produced at a lower activity. Now this is encouraged. So what is the value? What is this? Now the equilibrium value is less than 10 to the minus 5 atmosphere, means like 10 to the power minus 6. So now what? It is easier to oxidize. So just if exceed 10 to the minus 6, then oxidation will take place. You don't have to exceed 10 to the minus 5. Just 10 to the minus 6 means like 10 to the minus 5.5. Exceed this 10 to the minus 5.5. Under this condition, metal will be oxidized. Under this condition, it will not. Here actually you have to exceed 10, more than 10 to the minus 5 means like 10 to the minus 3, minus 4, etc. This is the situation. That means this is a great impact in steel making and iron making. Suppose AM is your silicon. You want to, or phosphorus. So you want to remove this to a greater extent. High degree of removal, dephosphorylation you want. Then what is the idea? Here, produce the product in a low activity. How? By fluxing it. Like calcium oxide, a basic, they are being acidic, a basic oxide, namely calcium oxide. Then this product, namely P2O5, namely SiO2, will be produced at a lower activity. As a result, this reaction will actually, the extent of this removal will be more. Okay, but this is the preliminary discussion. This shows. So these are the concepts. This is actually anyway whatever I have said. Chemical metallurgy field. Second is physical metallurgy field. The importance of solution thermodynamic study. Physical metallurgy. First of all, I will say this is required in construction of phase diagram. This study will help us construction of phase diagram. Phase diagram. Second, it gives activity versus composition and activity, what is this called? Free energy versus, let me write this. I'm coming to that. Free energy means gives free energy. Free energy versus composition and activity versus composition diagrams. This we can draw. Relation. Okay. Relations. diagrams, relations, right here, relations. Relations or diagram. Third is, this is required in solution model. To solution model, different model will consider their solution thermodynamics will come into help. This another is concept of activity coefficient. Etc. 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 The others will discuss this. So this is the importance of solution thermodynamics we have started today. So next actually we will take up the I say introductory terminologies, but we'll consider this. Okay, let me rub off this part. This is over satisfactorily. So I'm once more giving the caption, so important, solution thermodynamics. So first is different, we have to, let us be introduced with different concentration units. First, I give this mole fraction. First, mole fraction. Mole fraction, the symbol is, we use xi is what? Even for the subject reference solution, multi-component solution, namely I, J, K, and so on. You know that steel is actually multi-component solution. Hot metal is. So mole fraction is what? Xi is what? Mole fraction of I, the species I. So what? Ni plus Nj plus Nk, okay, and so on. It goes like this. What are these? These are the moles. Moles of I, moles of J, and moles of K. Moles of K. So this is the moles. This is the Xi. What is this mole percent? Mole percent I is nothing but, this is actually total moles. The mole fraction, you know, already I have discussed. Mole percent I is mole fraction, okay, mole fraction I times 100 times 100. So you can write xi times 100. Second is weight fraction, weight or mass fraction is what is actually this. I'm not giving mass fraction of I. What is this right here? Wi, mass of I or weight of I. Wi plus Wj plus Wk and so on. This is, you can write what it is, weight or mass of I, mass of I, mass of J, mass of K. So this is the weight fraction. So weight percentage, then what will be? Weight percent I is nothing but weight fraction of I times 100. I'm not giving any symbol for this, not needed. Okay, just if we write this. Okay. Third, next is a different constant unit structure. Next, I will consider interdependence of mole percent I and weight percent I. Very important. So how will you get this? Suppose you want to get mole percent I. Again, remember the system is multi-component I, J, K, and so on. Oh, by the way, yes, right. Is what? From weight percent. You know the weight percent. Get the mole percent. How? Is weight percent I divided by atomic weight of I. Atomic weight of I. And next, in the denominator, weight percent I, atomic weight of I plus weight percent J, atomic weight of J plus weight percent K, atomic weight of K, atomic weight J, maybe a subscript may be better, atomic weight of K, and it goes on. If it is I, J, K, L, M times 100. This is the relation. You can give a box, so important. So you can give a box here, important. Note, I have written here atomic weight I. Note, atomic weight will use atomic weight I. You will use atomic weight of I when elements are considered in the solution. Elements are considered like iron, manganese, silicon. Here atomic weights will be involved. When we but when we use compounds like CaO, MgO, CO2, etc. Then obviously the molecular weight will be considered. One thing easy to remember here, if you have difficulty, so how you will get, if you know weight of say iron, how will you get it mole of iron? Then you will remember from weight to mole, weight, iron weight say 112 grams. What is the mole or mole or gram atom of iron? You have to divide by the atomic weight. So that's why division. See, in contrast, that's why division takes actually weight to mole. Here the converse. Converse is what? Weight percent I. How to find from the given mole percent. So I am writing mole percent I. Now this time will be divided. 1 gram mole it should be opposite. It times atomic weight of I divided by mole percent I times atomic weight of I plus mole percent J times atomic weight J plus mole percent K times atomic weight of K and so on. Again, so from moles to gram mole to gram, you have to multiply by the atomic weight. So this is the logic. So easy to remember. Times, of course, since it is a percentage, this is a fraction. This fraction times 100. This is another one that you can put inside a box. So introduction is over and introductory terminology is also, or say concentration, different concentration units are all over. Next I shall take up Raoult's law and Henry's law. Raoult's law first. So next is Raoult's law. Raoult's law, what it says? Raoult's law. What it says? The relative lowering of vapor pressure of a solvent, of a pure solvent is equal to the mole fraction of the solute. This is Raoult's law. So what does it mean? I say consider a binary solution. AB. A is the solvent, B the solute. What will happen? A has a pure solvent has a vapor pressure, So this actually leads to, so his vapor pressure is PA0. A moment ago we are writing PZN0. This is the saturated vapor pressure. This will be reduced the moment, because it is for pure A. The moment B is added, vapor pressure will be reduced. So vapor pressure, remember, functions of three things I have already told. One, you understand that temperature is vapor pressure temperature relationship you know very well. And this PT diagram itself shows. And the effect of pressure I have discussed also last class maybe, and previously also. And now composition. Composition also, other things same. Composition changes 80%, 100% to 80%. Vapor pressure changes. So remember, vapor pressure is a function of temperature, pressure, and composition. This I mentioned somewhere, but so I'll take up this. So PA0, it is now reduced to a lower value, PA. And relative means divided by PA0. This is This, according to Raoult's, is equal to the mole fraction of the solute. B is the solute. Or continue, 1 minus Pa by Pa0 is Xb, is 1 minus Xa. You know this binary system, mole fractions add up to 1 mole fractions, because sigma xi in a solution, sigma xi is 1. So Xa plus Xb is 1. Xa plus Xb is 1. 1 minus Xa. So you have 1 cancel, minus cancel, or you get Pa by Pa0 is Xa. Continue. What is activity? What is activity of A? Activity means there is a reference set. Activity of pure activity of A. Activity of pure A, we know one. Activity is what? Tell me the basic definition, starting definition. Fugacity of A at the state under study divided by the standard state. Activity of A at the state under study relative to the standard state. This is the whole definition. Remember this, we said vapor pressures are so small, the fugacity and pressure are same. We write for low pressure, fugacity and pressure same. We can consider they are almost same, and because they follow ideal gas equation. Low pressure vapor pressures obey ideal gas, so fugacity is pressure. For real gas, actually we consider. So it is, if we consider this, Pa by Pa0. So what you are getting? I'm sorry, Pa0. This leads to what? That means activity of A is Xa. This is the famous relationship of Raoult's law. Activity is mole fraction. This is similarly, activity of B is Xb. This is Raoult's law equation, expression, Raoult's law. After Raoult's law, activity is mole fraction. Okay, so activity of A is Xa, activity of B is Xb. Raoult's law, the solution which obeys, note, the solution which obeys Raoult's law is called ideal solution. It's called ideal solution. So now actually we go up there, which are not needed. Ideal solution. So for non-ideal solution, what will happen? That is solutions which obey, that is solutions which deviate from Raoult's law. Solutions which deviate from Raoult's law for non-ideal solutions rather, what is the expression will be modified now. Activity is no longer mole fraction because it is non-ideal and non-Raoultian solution. Non-ideal, non-Raoultian. So what it is then? It should be modified by an by a property called activity coefficient is gamma A XA. What is this? This is known as activity coefficient. Activity coefficient of A. An activity coefficient can be two types, gamma A or gamma I am writing in general, gamma A, similarly activity of B is gamma B XP. Anytime you see, you follow one thing. I'm going back here. Activity is mole fraction, very simple, but you should note that activity means it has a reference state. Without reference state, activity has no meaning. So what is the reference state? You can clearly go to this here. Pure state as the standard state. Reference state. Pure state. I mean, this we have already used this pure state standard state. That means we actually consider Raoultian standard state. Raoultian is the conventional standard state. Pure state is the standard state. If you ask me, are there any alternative standard state or different standard states? Yes, there are. And we have to consider them later on. Alternative standard state based on Henry's law and so on. There are alternative standard state, we will consider them, okay, to a great extent, okay. But for the timing, pure state is the standard state. And recall what is the standard state for solid? Pure solid. For the liquid, pure liquid. For gas, pure gas. And this also you have to add 1 atmosphere, 1 atmosphere, 1 atmosphere. This is this conventional standard state. Today we understand this is a Raoultian standard state. Now, now gamma I, instead of A and B, A or B replaced by I, not bad, I. Gamma I can be greater than 1. Gamma I can be less than 1. When this happens, this is called positive deviation from ideality. This leads to positive deviation from ideality. Ideality means ideal solution. Ideality. And this means negative deviation from ideality. Now, one thing very interesting, why you consider positive? Gamma I greater than 1. Greater than 1 means 2, 3 positive. Less than 1 is also maybe positive. It's like say 0.1, 0.2, 0.3, all positive. 0.001, all positive. So then why negative? The reason is this, you have to understand, because I am writing here. This is enthalpy of mixing is positive. This is actually something you have heard of this, gives energy of mixing, enthalpy of mixing. So you write enthalpy of mixing, like say H is actually partial molar enthalpy of mixing. Enthalpy of mixing, or strictly this is elaborately partial or enthalpy mixing Hi by m. That is or that is partial molar enthalpy of mixing. That is partial molar enthalpy of mixing, a short form enthalpy of mixing of I. Enthalpy of mixing of I. Partial molar enthalpy of mixing of I. Partial means component wise, or integral means you have to together. So Hi bar m is what will happen is, why it is positive? Answer is not because greater than is, this is positive. If you want to recall what is this, I discussed it like Gi bar m is Hi bar partial molar enthalpy minus enthalpy at standard state. This I will discuss in details, okay, maybe next class. Enthalpy of mixing, positive. Then is positive, this is. And what it is this? What this is? here, right? I don't have space here. Enthalpy, right? Partial molar enthalpy of mixing is, as you say, is negative. This is positive, that's why positive deviation. This is negative, that's why negative deviation is negative. Okay, here again the partial molar mixing of I is negative. These are the things. Now tell me, now I can remove few more lines here. For comments, comments. Comments. For Raoult's law, or Raoult's law, Raoult's law, or say this way, right? For Raoultian solution, Raoultian solution means the solution which obeys Raoult's law. Or the which type of solution, you know, that is ideal solution. This is ideal solution. What is you get? What is the gamma? What is the equation? Remember, AI is in general, AI is xi. We have seen AI is xi. So what is the comment? What is the value of gamma? That means automatically gamma I is how much? It is greater than 1, positive deviation, less than 1, negative deviation, and when there is no deviation, Raoultian solution, gamma I is 1, as we say, like this. Follow this. So this is, now if you want to sketch Raoult's law, plot Raoult's law, Raoult's Raoultian solution, Raoult's law. Very easy. Yeah, plotting is very easy. Very easy equation. Activity is mole fraction. So what is this? Right. So I am plotting AB. I am considering unless mentioned binary system. Right here, binary. Iron manganese. Okay. Binary Copernican. Binary system. AB. A binary solution. AB plotted against XB. You know, mole fraction in the binary, you know, XB starts from 0 and can go up to 1. When it is pure, this is 0. And AB likewise, AB is XB, so it is also 0 to 1. And what is the line like? A curve like? Straight line passing to origin. Straight line. Activity B is XB line. Okay. And similarly, if you consider activity of A on the same diagram, then do one thing. You write XA is what? The other way. When XB is 1, then XA is 0. And when XB is 0, XA is 1. Activity of A is 0 to 1. How will you sketch this? You, of course, excuse me. So what is the equation for this? A is XA. Take a look. Yeah. So you can give this. This refers to this y-axis, and this refers to. I'm sorry. This correct. And I'm sorry. The same. Here, this refers to this axis AY. This y-axis, and the x-axis is clearly shown. So this is the Raoult's law equation. Now another thing is this. Now deviation from Raoult's law, how will you show this? This I wanted to show. Now this is Raoult's law. Now how will you show? Let us plot the deviations from Raoult's law. I am drawing this for say again AB. You may first draw the Raoult's law for reference, then show the deviation. This is the one. I am drawing this line. Okay. So what is the Raoult's law? Just faintly you may draw. Okay, I have drawn it. Okay, a solid line I have drawn, a bold line I have drawn this. Okay, this is AB is XP. What is the deviation? Is gamma greater than 1. So activity is gamma B XP. So you greater than 1. This is you can write this is AB is XP as before, and this is AB is gamma B XP. Gamma B greater than 1. See, greater than 1, that's why it is activity of B is greater than XP. So here activity B is XB and here activity B is greater than XP because gamma B is greater than 1. So this one thing you note that at high concentration when XB tends to 1, then it merges with the Raoult's law. So like say 0.99, 0.95, mole fraction is 0.94, then it is merging with the Raoult's law, means at that point activity of B is XP. Suppose it is 0.99, 0.99. So this is see merging, but here the greatest here. So this is one. So positive deviation, as I have told you, okay. Then you can draw for another one, and if you increase the temperature, 3 I am drawing, 3. Noted this. This is as temperature increasing. If you increase the temperature, this activity, which will be affected? Let me write beforehand. Gamma I, note, gamma is a function of course, like everything, free energy, activity, fugacity, everything, function of gamma here now. Gamma is a function of temperature, position, pressure I should write, but see, you know, the pressure effect is small. Pressure effect is small because on the condensed phase that you have studied. So temperature composition. So gamma as temp, and also note as temperature increases, the deviation decreases. Deviation from Raoult's law. Raoult's law means ideal solution. Raoult's law decreases. That is, the curve more approaches toward the Raoult's law line. Gamma will be changing. So you see gamma here, as we increase the temperature, see the curves gradually moving towards the Raoult's law line. This is Raoult's law line. Moving towards the Raoult's law line. So this is the of these three, which has the greatest deviation? The top. at the lowest temperature of these three. As temperature increases, deviation decreases, and merging takes place with the Raoult's law at an earlier concentration. Higher concentration always, but at earlier than before. Like here, now it is here. Again, it is still increasing temperature. Again, deviation decreases, and it is moving towards the Raoult's law. If you consider a solution called regular solution, it will never reach, but we try to tend to reach. It takes infinite temperature to exactly reach. So this part I am not discussing much, but this will be enough. Now, so this is the figure. Next is obviously this is the positive, right here, positive deviation. Positive deviation case of positive deviation. Remember, this is Raoult's law, these are the all deviations. And remember, when they merge at high concentrations, have I written this? At high concentrations, like note also from this figure, note also as Xb tends to 1, AB also tends to Xb, means AB is actually merging with the Raoult's law line, which is AB is Xb. So AB tends to Xb, and which is tends to 1, means AB also tends to 1, like this. Example 0.95. Xb is 0.95, AB is also 0.95, right? AB is Xb because it follows line. Note, as remember at high concentration, as Xb tends to 1. Not here, clearly see this is much different from this. Much different, placed actually much above this. And so this happens. So this is now negative deviation. Negative deviation. Similarly, just similarly, you draw first the reference activity of B. I am showing for activity of B. It can be, you can draw for activity of A also similar manner. So like this. So if this is this way, then this will be this way. Positive deviation. I am not going to this this I don't want to make this complicated or actually illegible or clumsy. This again you consider 0 to 1, 0 to 1. So again you have a reference of not good. Sorry, this is better this side. So it is satisfactory. This is again Raoult's law line, ideal solution. Raoult's law. What is negative deviation? This is positive deviation. Why gamma is greater than 1? Gamma will be less. If gamma greater than 1, activity will be less than X. Right? Shall I write somewhere? If gamma greater than 1, positive deviation have written anywhere. Gamma be greater than 1. So that is, and where I wrote Raoult's activity is gamma b xp, gamma be greater than, and where I wrote now I shall write. Very good. The negative deviation, again deviation much, then gradually merges with a high concentration, then increase the temperature, deviation less. So if we increase the temperature, this temperature increasing, temperature increasing. All systems behave ideally. Remember, it is like this: temperature increasing, it is moving towards the Raoult line. Temperature increasing, and what is this activity? This is what activity of B is gamma B xp, right? Like this is gamma B xp, and only thing you have to write gamma B less than 1. Another comment you may write here, that is good comment. If it is greater than 1, that is activity of B is greater than xp. As you see, this activity B is xb and these are greater. For given xb, it is greater. Here, for given xb, this is the activity of B is xb, Raoult's law is less than. So that is activity of B is less than xp. T increasing, okay, T increasing. So note, shall I here? Note, where shall I write note? I have written perhaps. This is general as temperature deviation from. Note, this is valid for both positive and negative deviation. Not only for so what I have said here, as temperature increases, this is increase, not pressure. As temperature increases, deviation from Raoult's law decreases. All this way, both cases. It's a decreases, means towards Raoult's law. Decreases, deviation decreases towards Raoult's law, moving towards Raoult's law. That is, the curves move more approaches more toward more toward the Raoult flow line. This is valid for both positive and negative deviation as shown here. Okay. Next is, I will give you the properties. I'll give you the properties. So just remove this. So summarize, in a sense, summarize this. Okay. Summarize this. Summary. Properties of ideal solution, solution with positive deviation, and solution with negative deviation. Solutions with negative. Okay. What I say is ideal solution. First try. Ideal solution. This is Raoult's law, right? In bracket, Raoult's law. A. First case. What is this properties you already got? Tell me. Okay, sorry. Give this. A is what? AI. Instead of A or B, write I. AI is Xi. What is the implication? Give this gamma I is 1. What else? Activity, recall, I have removed this unfortunately activities Pi by Pi0. Recall. Right, I'm writing here. AI, in case you have forgotten, Pi by Pi0. Remember, fugacity ratio from which you get vapor pressure ratio. So Pi by Pi0. So Pi is activities. So Pi is Xi Pi0. Happy. This, what else you can write? keep on writing whatever you can write. H I bar m, sometimes we write delta H I bar m, okay, or sorry, or this I already told, sometimes delta H by delta is redundant because mixing means a delta, mixing means change. So I'll not write H I bar m is what, tell me, is what, 0. This I forgot to mention here. I mentioned that for positive deviation it is positive, for negative deviation it is negative, but obviously it means for ideal solution Hi bar m is 0. And another important property is the bond energy. Bond energy is what? Let me write. Bond energies are negative normally. Yeah, normally negative. So we get mod numerical values of the AB. See, A and B are present in the system. AB solution, binary system I have written somewhere. Ideal solution. Ideal solution of binary systems. In binary system, is bond energy is average of these two, like atom bond energy mod plus EAA, for example, EBB is average. Sorry, average of this. So this is bond energy of A and B. Bond energy is, remember, bond energy is considered 0 at infinity. So when they come closer, it becomes negative. All bond energies are negative. So that's why I have taken this. When these like atom bond energies, average of this like A, B, B is exactly equal to the unlike bond energy, then this happens. These all results. These are all interdependent, okay, or concomitant. This thing. So okay, very good. Second. Achha, Pi is xi, Pi 0. I'll give a sketch here since I have enough space. Try to follow. This picture I'm showing. This picture I'm showing. Say A pure liquid. A liquid pure. Okay. Achha, I have written I pure liquid, and there is a I vapor. There is I vapor. What is this pressure? What is this pressure? What is this? I vapor pure. I liquid pure. This must be mentioned pure. Then what is the vapor pressure? You know very well, it is called Pi 0. When you when you change this to make it impure, I is no more impure, Ij liquid, right? Impure I, solution I, impure I, solution I, mixture I in alloy. So what will happen here? Again vapor. There will be some vapor. No one can stop. I vapor. What it says? Raoult says lowering of vapor pressure. It will be Pi, and noting that Pi is less than Pi 0, and is given by what? Pi is xi Pi 0. Xi is what? This is a mole fraction here. Xi is obviously very easy. Is nothing but Ni by. This is very easy. Ni plus Nj in the liquid phase. So this mole fraction here gives, actually decides this vapor pressure. This is mole fraction times the pure liquid vapor pressure, and mole fraction is actually, this is impure, less than 1, so Pi is less than Pi 0, Xi is less than 1, so very easy to follow. This is Raoult's law. This is the Raoult's law. Second, complete the chart. What will write? Non-ideal solution. What you will consider? Deviation from Raoult's law. Positive, say first we consider positive deviation from right? Full positive deviation from Raoult's law. So again, you write the properties. You can write yourself. Ai is no more xi but rather gamma I xi. Where you know it is gamma I is what? Greater than 1. And of course you have to write this, okay. Activity is, recall what is activity, this means what? This means what? You write also gamma ai is greater than xi. Easy to say. If ai is xi, then what you are getting here? Pi by pi0 is greater than xi. That leads to pi greater than pi0 xi. Try to follow this. So ai is greater than xi, so pi is greater than pi0 xi. So what is the difference between this? This is pi is just equal to xi pi0. This is greater than xi pi0. Vapor pressure. So vapor pressure in this case, I'll sketch this, but let me finish this first. Hi bar m, what shall I write here? Tell me, as I've already told you, is positive. That's why positive deviation. That's why positive deviation. And last is what? I don't have space here. I'm writing this one here. Guess which one will be greater? It is no more equal. It's not equal to, but which bond energy is greater? Positive deviation means like atom bond energy is greater. So what is this then? Like is, this is greater. Half EAA plus EBB. Half, oh, too many. Then you get third bracket. What I did there? Okay, too many brackets. Okay, oh, that's great. Oh, repeat this. Repeat. Half EA. This mod actually itself serves as a bracket. Like atom bond energies are greater. In that case, positive deviation will occur. And what is the other consequence? Vapor pressure will be greater than pi0 xi. So what is the vapor pressure here? In this case, pi is what? Right here, what is this? Pi is what? Tell me, right here. Pi0 xi. See, pi is here. Pi by pi0 is ai is xi, so pi is pi0 xi. This is greater than that. Tell me vapor pressure that you have here. Okay, so we'll take an example. Suppose, tell me here. Suppose I ask you. Suppose pi0 is 0.03 atmosphere. Say 0.03 atmosphere, and xi is say 0.2. Means 20% of I and 80% of J. Okay, this is what Ij. Okay, very good. So what is the Pi? What is the Pi then here? Pi0 is, this value is 0.03. Because right, it is 0.03. It cannot be any more 0.03 less than that, because it has been diluted. It has been now made impure. Okay, it has been alloyed. So what is this value? This is what you write here. What is the Pi? Pi is, write this nicely, less than pi0. What is that value? Pi0 xi means 0.03 times 0.2. Sorry. 0.2 is 0.006 atmosphere. So write that 0.006. Vapor pressure has decreased. Thank you. 10 minutes. So where I am? So 0.06. So you know vapor pressure changes. Acha, very good. Now in the the second case. Second case is what? 0.0066. Okay, very good. Again, second case, then what you write here again? Pi0 cannot be changed, pure 0.03 atmosphere. What is xi? Again, you cannot change that, 0.2. What is the consequence? Pi is what? Pi0. Pi is what? Tell me. Greater than. no more equal, not equal, greater than. From you follow this relationship, you will greater than. Pi 0 xi is this, that is greater than what? Pi 0 is 0.006, 0.006 atmosphere. Eg say greater than 0.06, 0.008 atmosphere, 0.008. Okay. Achha, why? Increase a little bit more. Okay. Say 0.01. Say 0.0. That will be more. Is it 1 point I want to establish? This is the second case. And what else I have said? Bond energies, like atom bond energies. C is what? Non-ideal solution. Negative deviation. From Raoult's law. What is this? You write similarly. AI is gamma I xi, and gamma I this time is less than 1. This AI is less than xi. Happy? And also see, this is less than xi, or pi is, pi means pi is this one. This is the pi. And this is for liquid, this is the pi 0. But only two things are there. Pi, that is, you write here again, pi is less than xi pi 0. See the change. Xi pi 0. So here pi is xi pi 0. Here pi is greater than pi 0, xi pi 0. Here less than. And what else? Hi bar m, partial molar enthalpy of mixing, is negative. And what else? Very important, bond energies. You have to enter into the atomistics when you are studying solutions. Which is greater now? Which is stronger? I'm sorry, which is stronger? Now, negative deviation means unlike bond energy is greater than the like ones. So this will be greater than half of this like bond energy. I'm very sorry. This plus mod, all mods, so that positive numerically. When they are considered numerically, so positives, not algebraically. So these are the contrast. Now if I do this job here I have done here, so 0.06. So follow, this is for ideal solution, this is for positive deviation 0.01, 0.006, 0.01, and here what it will be. Again try again. Pi 0 cannot be changed because pure liquid is 0.03 atmosphere, and the comparison you have to make with the same composition. Xi is 0.2, so that you will understand. Now what is, apply this. Pi is what? Here see, Pi is less than xi pi 0, that is less than 0.006 atmosphere. Eg, for example, what? Less than 0.06 means 0.007 atmosphere, or 8 atmosphere, 8 atmosphere. So see, pure A, first of all, no solution, means all condensed phase is pure, as we have discussed previously up to assignment number 7, all pure state, silicon carbide, all these things, nickel oxides, tin oxide, all pure, no solution. Solution begins from today, solution thermodynamics. What is happening here? Like I say, so pure 0.03 atmosphere. And yes, I have considered a solution of Ij where I is, mole fraction of I is 0.2, means percent-wise 20 mole percent, and the other J is 80 mole percent. So Xi 0.2. what is the vapor pressure? You see, vapor pressure is reduced. This Raoult's law has been stated, but the value is actually what? What is the value? Pi is Pi 0 xi means 0.006. Of course, it is reduced, but this is the ideal. When non-ideal is plotted, this vapor pressure of I. For example, positive deviation, where Pi, so Pi 0 is 0.03, xi is 0.2, Pi greater than is greater than 0.06, not this anymore. Pi is 0.06 atmosphere. If I write, that would be a good idea. Atmosphere, you write 0.03 atmosphere. This is atmosphere, and mole fraction is 0.2. Mole fraction has no unity law. So that means greater than 0.0. Have yes, correct, 0.006. Any value more than that, take an example 0.01. So which was 0.0 start? This is for pure 0.006. This is impure. So 0.01 greater than this. Here this point greater than this. Then what is this when it is negative deviation? It is less than. Okay, Pi less than. For example, oh, what have you? Sorry. Less than 0.06 means 0.00, 0.003. Okay, what you have written here, and greater than. 0.0 less than means I am very sorry. 0.003. So again repeat, 0.006 start pure, no solution, no impurity, no nothing, liquid. Like say pure zinc. So pure 3 vapor pressure. Then becomes 0.06 if it enters into a solution with positive deviation. I am very sorry. I repeat, this is for the pure. So zinc, pure zinc. When zinc is actually okay, they is allied with J. Then what is the vapor pressure? 0.006. But this is reduced as it should be. Raoult has also quantified this value. It is a reduction. Now, in these two cases, what are the values? So Pi is here in this case, since Pi it is greater than 0.06, 0.006, say point. So 0.006 becomes 0.001, and here it is less than 0.003. There is no problem here. This is it. There will be once more query here. It is greater than this. Can it be? Say answer this. It is greater than 0.0. So any value can be. Can it be ever 0.03? I have written 0.01. Can it be 0.03? Can't be. 0.03 is for the pure. This is an impure. It is an alloy. Is vapor pressure will be 0.03. So only thing is greater than 0.06. The vapor pressure in the. So, but this can never be this value. It is impossible. So be careful about this. And this is of course less than 0.06. So no contradiction, no completion of this. One thing I will tell you, this may be a little bit crude, but this is actually something thought myself. What happens if here bond energies AB and like atom bond energy and unlike bond energy same. So it is actually a kind of ideal solution. Ideal is no bias. Bond and no bias. So as a result, what happens? What vapor pressure we get? Following this character, no bias. I actually escapes into the vapor phase. With what value? No bias, 0.006 atmosphere. Considering here positive deviation means what? Like atom bond energy, like atom bond energies are greater. Like atom, because similar atoms. Like atom, okay, prefer themselves, okay, not unlike. Like bond energy is greater than like unlike. So like of which, suppose if you have a positive deviation, what happens? If you have I Actually, I, if you add in positive deviation, you would, if suppose you have a I, species I, and if you give J, then what will happen? Positive deviation means it doesn't like J. It likes I only. Similarly, J likes J only. Like have the preference, bond energy, greater. So like atoms, okay, prefer each other. So we are considering I. So I actually see what happens. You have given J. So I do not like to be with J. Okay, this is the one I wanted to arrive at. I, since there is positive deviation, don't like J, because their interaction I like atom interaction is greater than Ij. So they don't like, as a result of, since this of this stranger of this impurity is in the presence of this, it doesn't like the presence of J. So what it does then, as a result, I I actually escapes into the vapor phase. I escapes into the vapor phase because I don't like this, okay, J. So escapes more into the vapor phase. What was 0.006, now it has been 0.01, because this is reason is this bond energies, okay. Like atom bond energies are greater, means unlike is less. So attraction is less, likelihood of their coexistence in the solution state is less. So this try to move to the gas phase more. As a result, we see this happens. And opposite happens, negative deviation means A likes B. So much likes, it doesn't have so much actually interest, I should say, so much tendency to go to the gas phase. Because A likes B, bond energy is greater. So very good, welcome. So as a result, what happens? A doesn't go to the go to the vapor phase, but with a lesser extent, namely 0.003. This explanation maybe you may think of, okay, it may be helpful. Okay. Last I say, last additional comment. Additional comments. This will then complete this topic, and we will actually call it a day. What is this? One. What is the consequence of positive deviation in the phase diagram? So in positive deviation systems, tendency of clustering of phase separation, phase separate, because like attract like, not unlike. So like one phase is alpha phase, another is beta phase. Phase separation, we may use the term clustering increases. In positive deviation system with greater positive deviation, in positive deviation system, clustering occurs, tendency occurs. And obviously, if the positive deviation increases, extent increases, then there will be finally complete phase separation. Second will be opposite. In negative deviation system, what will happen? Here clustering means A likes A. So A clustering means alpha. A B clustering means B and is beta. So alpha beta separation. maybe two liquid separation, okay, in monotectic systems. This I don't want to enter into now, okay. So liquid immiscibility. So separation, each other, they love the AB bond energy. So what is this? Chemical compound formation, tendency of chemical compound, or which you call ordering, like say compounds, say calcium tin, Ca2SN compound formation or intermediate phase, or say ordering, order structure is the compound or order structure. Sodium chloride order structure, cesium chloride order structure. So in what is the tendency of, tell me, chemical compound formation or ordering. This line is visible. This line is visible there. Chemical compound formation or ordering takes place, occurs. Negative deviation occurs means if occurs. That's it. With this, actually, we have completed this initial part of this solution thermodynamics study. So we'll actually now call it a day. Thank you very much for your patient hearing and for your cooperation. Thank you very much. Okay, see you next class. Thank you. Bye. Bye. Touch the same one. রেড আছে তো, যেটা ছিল ভিডিও, যেটা লাল হয়েছিল তখন।
লাল তো কিছু, এই তো প্লে হচ্ছে, এই তো টাইমার তো যাচ্ছে, ঠিকই তো আছে।
কোনটা স্যার ভিডিও ছিল? ভিডিও দিয়ে কোন দিয়েছিল?
এটা করে দেবো।
ভিডিওটা তো কোনটা ছিল, মানে ভিডিও
মাঝখানে ছিল, সেটা চলে গেছে
প্রথম থেকেই। হ্যাঁ,
হ্যাঁ,
এটা
এটাই হবে।